This lesson is section 1.6, and as you can see, we are going to be solving systems of equations, and we're going to learn or review three ways really. One of them involves a solution from a graph, which will hopefully, if there is a solution, it will be the intersection of two lines, and we'll look at some other solutions or non-solution answers from a graph. And then we refer to two other methods as solving algebraically, and this is involving the substitution method and the elimination method. So we're going to look at a few graphing examples first. First of all, what is a system? Well, it's two or more equations with the same variables, and the solution to a system will be two numbers, an x, y, an ordered pair. And the key is that those numbers that we find for x and y not only must make one of the equations true, those two numbers have to make both of the equations true. Alright, so I want to walk you through an example. This first example is really a good illustration of some of the hurdles that we have to overcome when we are graphing, especially when we're not using a graphing calculator. But this is good experience. We're going to touch on some maybe tips that may help you when you do cross or try to cross some of the hurdles that sometimes we run into when we solve by graphing. Well, let's just start off with what we typically do when we're given a linear equation. We want to look at it in slope-intercept form, which means to solve for y. So this top equation, solve for y, will be, first of all, I'm going to add 3x to both sides. 8y is equal to 3x plus 36. And then going one step further, I'm going to divide by 8 on both sides. Y is equal to 3/8 x plus 36/8. And we can reduce 36 over 8 to 9 over 2, which is another way of saying 4.5. Okay, and we'll do this line in just a moment. Y equals 3/8 x plus 9/2. We'll do that in red. Okay, and then the other one, let's just go ahead and, while we're here, we'll solve it for y as well. We'll just keep it in blue so we can keep the lines maybe straight, distinct. Solving for y here can be done in one step. So y equals negative 6x minus 21. Okay, and that will be our blue line. Okay, well, right off the bat, I'm going to start with the blue line, and right off the bat I notice one issue. I told you earlier, we have some hurdles sometimes that we have to cross when we're graphing, and here's one of them. We've got to be able to make negative 21 fit on our graph. The y-intercept of that line is negative 21. Well, you can change these, and we've had to do this in the past, and it's going to come up more in the future. We need to change our scale so that we can fit negative 21, and even though really there is no wrong answer, I like to stick with numbers where I can get exact points on a grid. For example, if I let my y-axis be in 3s, notice I've decided on 3s for the y-axis, so if you do this, you need to tell me in some way. Either you can write on each line if you want, but it's not necessary. Just point to that axis. If these are in 3s, then negative 21 would be down 7 marks. 3 times 7 is 21. So this would be a y-intercept of negative 21 on my graph, since the y-axis is in 3s. And just to be consistent, I'm going to make the x-axis also in 3s. Okay, makes it a little bit easier when we're determining points on a line. Alright, so I notice now, using our typical rise over run from the y-intercept, I notice that the slope, or rise over run, is negative 6. Well, negative 6, I could do up 3, up 6, that's positive 6, and then I would need to go left 1. And I don't really know for sure where that is, and I'm the type where I don't really like to guess. I can pretty much, I'm in the ballpark here if I just move over to the left a little bit. But let me give you, here's another example of just a little bit of a hurdle that we need to cross. I want a slope of -6, but let's think of that in terms of a fraction divided by 3, a number divided by 3, since our units are in threes. Okay, that's easy enough to think about. Let's think about a number in the numerator, and obviously that would have to be -18, or I would have to do it as 18 over -3. Either way, I get -6. Well, now I can count these out using the grid marks that I have laid out on my graph, and it's nice and easy. If I wanted to go up 18, that's really like going up 6 marks. Okay, 3, 6, 9, 12, 15, 18. And then left 3 is really a slope of -6. Okay, as long as the fraction equals my slope, it really doesn't matter what fraction I use as long as it equals -6. And then we can just do that same thing, up 6 and left 1. And I've got 3 really good points now with which to draw my line through. So let me get my line draw tool. You will get your straight edge and we'll connect those dots. So here's my blue line, y equals -6x minus 21. Okay, well now let's work on the red line, and I'll change this into red. Let's start off the same way. 9 over 2, of course, is the same way as saying 4 1/2. All right, and that's on the y-axis. That's a y-intercept. Okay, here's 3. Here's 6. 4 1/2 should be halfway between. So I'm going to let that mark represent the halfway mark between 3 and 6. That's 4 1/2. And then counting the slope from there, like we did before, 3/8. You know, this would be 3. One full space would be 3. But going 8, that would be 3, 6, 9. I guess I could figure that as being 8, just short of the 9 mark. That could be 8. But that's really, I mean, that's okay, but I wonder if we can get a more exact point. Well, here's another option for you. And what I'm doing here isn't necessarily wrong. I'm just throwing several options out so that you can have them at your disposal when you're graphing lines. You can also graph by using intercepts. And we've already used the y-intercept, so that part's already done. We know how to look at this constant, and whatever that number is, we plot it on the y-axis. But what about using the x-intercept as well? Sometimes that comes in handy. Finding the x-intercept means we're going to replace 0 with y. So anytime you want to find the x-intercept, just plug 0 in for y and solve for x. Easy enough. Because that's really what you did when you found the y-intercept. You plug 0 in for x. And when you did, this whole term becomes 0, and you get y is equal to 9/2. So now just follow the same line of thinking. Finding the x-intercept, just let 0 go in for y. And solving for x, we get -9/2 is equal to 3/8x. And solving for x means we're going to multiply by 8/3. And I get -72 over 6 is equal to x. And that reduces, and it's a nice, easy to plot number because it's divisible by 3, obviously. -12 on the x-axis, I would go -3, -6, -9. Here's -12. So it looks like those dots all fall on the same line. So now I grab my ruler and I connect the red dots, and I'm looking pretty good at this point. except what is the ordered pair of this point of intersection? Because the solution to graphing, solving by graphing, is where the two lines cross. And I don't really know for sure. I mean, I can make a guess, but guessing isn't really good enough. I'm pretty sure that the y is -3 because they cross at -3, but what is this? Is that -4? Is it -3.5? I'm not really 100% sure. So to be sure, in cases like this where the graph really doesn't give me a 100% confidence that I can tell the solution from this point of intersection, I'm going to rely on other methods, and I'm just going to use this opportunity to review with you elimination. I could have also used substitution, which we will talk about in a minute. But here's an example. Here's a review of the elimination method. Okay, so going back to my original, -3x plus 8y is 36. And 6x plus y is -21. And remember, elimination, and we'll do some more of this in a minute, but right now I'm using another method to prove my initial method, which is another good practice to do. You can always double check yourself by picking some other method. Elimination means to cancel one of these variables with either addition or subtraction. And at the way they are right now, nothing just automatically cancels when I add like terms or subtract like terms between these two equations. But if I multiply the top equation by 2, then the top equation becomes -6x plus 16y is equal to 72. Okay, so let's mark that out so we don't look at 3 equations. And now, if I add all of the like terms across between these two equations, I will eliminate the x variable. X will become 0, the y will become 17y, and the constant on the right side will become 51. Solving for y, I get y is 3. Well, that was pretty obvious from the graph. Here is y is 3. So half of my solution, half of my ordered pair is determined. And now to find the x part of this ordered pair, what is exactly? Looks like -4, but I don't really know for sure based on the way I have my graph set up. So let's see. Let's let y become 3 in either of these equations. 6x plus 3 is equal to -21. 6x is -24. X is -4. So sure enough, now I've got confidence that, number one, I did the graph correctly, because the solution that I've got from my graph is reasonable with this other solution that I got using the elimination method. So a lot of stuff there. I'm not saying you have to do this every time you do the graphing method, but I wanted to take this opportunity to show you, number one, different methods of graphing lines. Number two, when the graph really doesn't give you complete confidence because the two lines don't just fall on a easily to determine grid point. In cases like this, you will need to follow up with some other method. Please don't give me a guess. Make sure that you know from proving it with another method, either elimination or substitution, exactly where those two lines cross. So I know I took a long time, but to me there's a lot of stuff involved that could help in future problems. So the final answer here is -4,3. All right, let's do another example. This one is solved by graphing. And I accidentally erased the system working on this previously, so I put it back for you. This is your example 1B, of course. Well, let's go through the same process we did before. let's solve this top equation for y. Maybe I'll just do that over here, and let's mix up our colors a little bit. This top equation I'm going to do using green. Let's solve for y. So I got 9y is equal to negative 3x plus 18, and then dividing by 9 all the way across, I get y is equal to negative 3/9, which is negative 1/3 x plus 2. Okay? And then maybe this one I'll just do in black. Alright, so let's solve it for y. Negative 3y is equal to x minus 6. And then again, either dividing by 3 or multiplying by negative 3 or multiplying by negative 1/3, I get negative 1/3 x plus 2. Do you notice that it's really just the same equation? So when that happens, we have a special way of writing the solution to this. Let's go ahead and draw the line. It's really just the same line. And this one's going to be easy to graph because we don't need to change our scale. Everything's in units of 1, and we can count the slope as up 1, left 3, or down 1, right 3, and connect our dots. And so that's the line. It's really the same line. It was just represented differently in the original system. But when we solved them for y, we discovered it's really the same equation. So here's the deal. Here's how we interpret the solution for this. Any ordered pair that falls on this line, we've identified 3 of them just with my dots here. This is 3, 1. This is 0, 2. This is negative 3, 3. That's just 3 of them. Any other ordered pair we could find on this line is a solution to this. The numbers that we plug in for x and y off of this line, not only would it make the top true, it would satisfy the top equation. Those same 2 numbers would also satisfy the bottom. Well, how many ordered pairs are on this line? Well, if you look at the ends, this indicates that this line goes forever and ever, just like a typical line does. So there's no way to ever come up with the number of solutions because we'll never get to the end, either end of this line. So when this happens, when it's really just the same equation given twice, we're going to call this an infinite number of solutions. And I hope you understand why, because there's no way to ever tell, there's no way to ever list all of the ordered pairs on a line because lines go infinitely in both directions. Okay? Well, let's try letter C. We're still solving by graphing. And so the top one's already solved for y. That's nice. Let's take a look at the bottom one. Solve it for y. 4y is equal to negative x plus 12. Y is equal to negative 1/4 x plus 3. Okay, looks like the same thing. So we have this same example as we had before. So if you run into this, basically it's the same equation given twice. Your answer will be an infinite number of solutions. Now, if you should happen to run into an example where the lines are parallel, like for example they have the same slope but different y-intercepts, like this. So this would be something like, well, it'd be a negative 1/4 slope. So something like this, I'm just doing a rough sketch, and the other one would go through negative 7. Same slope. Well, obviously parallel lines have the same slope. These lines are never going to cross if they have the same slope. They will never cross, and in cases like this we do not have a solution. Okay, so there's one of 3 things can happen when you're solving by graphing. You will have one solution where the lines cross. You will have an infinite number of solutions because it's really just a single line represented by it starts off looking like two different equations, but it's really the same. Or in cases like this, you will have no solution, where you have the same slope but different y-intercepts. The lines will never cross. Okay, so those hopefully will help you with the graphing method. So now let's jump into some examples of substitution. Substitution is all about solving for one of the variables in either equation and then replacing that variable in the other equation. Now you have choices. You can solve for x on the top or x on the bottom. You could solve for y on the top or y on the bottom. There's really no wrong choice out of these four, but there is a best choice. Okay, and here's what you want to look for if it's possible. You want to target the variable that has the coefficient of 1 if it exists. Remember, there's an invisible 1 in front of a variable that is like this, 1y. And the reason for that is solving for y in this case is it can be done in one step. All I have to do is subtract 2x from both sides and I've solved for y. All of the others will involve two steps. I will have to add or subtract, then I will have to divide by something. So if you can, and in this case it's possible, you are much better off. Hey. So to recap this problem, when you're solving by the substitution method, you always want to, if it's possible, to solve for the variable that has a coefficient of 1. It's much quicker, it's much easier. You would not be wrong if you decided to solve for any of the other three. It would just involve more work, and it lends itself maybe to a little more errors because you're going to be ending up with fractions, and that just, for some people, causes a mess. So my advice to you is, if it's possible, solve for the variable. In this case, you're solving for y on the bottom because it has a coefficient of 1. So substitution says solve for one of the variables in one of the equations and replace that variable in the other equation. So I solve for y on the bottom, I'm going to replace y on the top. And so we're going to be solving for x first. So 5x minus 3 times the quantity negative 2x plus 7 is equal to 23. So I'm going to distribute negative 3. I'm going to distribute negative 3 to this quantity, and that result will give me 5x plus 6x minus 21 is equal to 23. And combining like terms, I get 11x, and I'm going to go ahead and add 21 to both sides. 11x is equal to 44. So I get my solution for x, and that will be 4. So remember, the solution to a system is the solution for x and y. So we're going to write this answer as an ordered pair. I know what the x part of the ordered pair will be. Now I need to find the y part, and the easiest way in this case is to go to this equation that's already solved for y. If I let x become 4 in this equation, it makes it pretty simple to find out what the missing y coordinate is for this ordered pair answer. So y is going to be negative 2 times 4 plus 7, and of course that's going to be negative 8 plus 7, which is negative 1. So my solution for example 2a will be x is 4, y is negative 1. Just make sure you write your answer like that as an ordered pair. Here's example 2b, same instructions. We're going to be solving by substitution. So if you notice, we have a similar situation as we had in the previous problem. We have a variable that has a coefficient of 1, and that's the variable we need to solve for. So I'm going to solve for x in the top equation, and I can do that in one step. X is going to equal 7y plus 11. So once again, substitution means solve for one of the variables in one equation and then replace that variable in the other equation. So in the bottom equation, I'm going to replace x with 7y plus 11. And I'm going to initially find y. And then I'll let that number for y help me find x. So distributive property, this is 35y plus 55 plus 4y is equal to negative 23. Combined like terms, I get 39y. And I'm going to go ahead and subtract 55 from both sides, and that's going to give me negative 78. And dividing by 39 on both sides, I get negative 2 for y. Okay, so that's half of my answer. And the easiest way to find x is to go to this equation that's already solved for x and replace y with negative 2. Okay, replacing y with negative 2, I get negative 14 plus 11, and that's negative 3. So my solution, for example, 2b, is negative 3, negative 2. Okay, this next example is still substitution, but if you notice, we don't have a variable that has a coefficient of 1. So we're going to have to decide on another variable to solve for. And you're trying to find the one that is the easiest math involved. If you can find a way to divide by the same number all the way across, possibly eliminating any fractions, that's always good. But in this case, really doesn't happen. So I'm just going to take this bottom equation, and I'm going to solve the bottom equation for x. You may have thought a different way. There's really no wrong answer here as far as what to solve for. As long as you do the math correctly, you'll end up with the correct answer. So solving for x on the bottom, I get 6x is equal to negative 9y plus 15. And then solving for x means dividing by 6. Negative 9 divided by 6 is negative 3/2 y. Plus 15 divided by 6, obviously that reduces to 5/2. Okay, well again, solve for a variable and then replace that variable in the other equation. So I solve for x on the bottom. Now I'm going to replace x on the top. So 2 times the quantity negative 3/2 y plus 5/2 plus 3y is equal to 5. Multiplying here, I get negative 6 over 2, which is negative 3y. I get 10 over 2, which is 5, plus 3y is equal to 5. Okay, and this is kind of interesting. If you notice, the y terms cancel each other. And I'm left with this situation that basically says 5 is equal to 5. Interesting. The variable cancels, and I'm left with what is obviously a true statement. This is a true statement that 5 is equal to 5. So whenever this happens, the variable cancels and you're left with what remains is a true statement. Then this is another example that we showed back in the graphing method where it's really just the same line, and any set of ordered pairs that falls on that line would be considered a solution. So here we're back to this case of infinite number of solutions. And sometimes you can recognize this. You might want to be on the lookout. You can save yourself a little bit of trouble. Do you notice how going from one term to the next, all we did was multiply by 3? And if you can recognize that right off the bat, then you know that it's really the same equation. As long as you did the same operation, multiplication by the same number for every term, then it's really just going to be the same equation when it's graphed. It's going to be the same line. So there's my answer. And if you don't recognize that it's the same equation, just written two different ways, you come down to a true statement after the variables cancel, you'll know this is the way to represent your answer. Okay, so finally, my last set of examples involves elimination. We've already looked at elimination in a previous example when we were graphing. This first example is set up perfectly for elimination because all I have to do to eliminate, or we might use the word cancel, the y variable is to add these two equations together. Because if I add opposites together, I get 0. And so I'm going to show plus to show that all the way across. I'm going to add like terms. 4 plus 2x is 6x. This cancels out. It becomes 0. And over here on the right side of the equation, I get negative 6. So my solution for x is negative 1. And now I find y just like I did before. I can plug negative 1 in for x into either one of these red equations. I'm just going to pick the bottom one. 2 times negative 1 plus 3y is equal to 16. Go ahead and multiply by 2 times negative 1 here. Add 2 to both sides. I get 3y is equal to 18, so y is equal to 6. So my final answer for this first elimination example will be negative 1, 6. Okay, sometimes the terms don't just automatically cancel, and we looked at this earlier. So let's find a way to, the easiest way to cause either A or B to cancel with addition or subtraction. And so I'm going to pick, since I noticed that if I did 5 times 2, I would get 10, and that would make a match here. Then I'm going to multiply the top equation by 2. Now you may have been taught in previous classes to always create opposites so you can always add. And if that's the way you were taught and you're already comfortable with that, then that's the way you should stick with it. I'm not really particular. I'm going to let you decide whether you want to add or subtract. It really doesn't matter to me. Multiplying by 2 on the top equation gives us 6a plus 10b. Don't forget, a common mistake here, some people forget to multiply on the right side. Just everything gets multiplied by 2. I'm not doing anything to the bottom equation. And I'm showing minus because it's going to take subtraction the way I have it set up. It's going to take subtraction to eliminate b. So 6 minus 4 is 2a. And then negative 54, now this is tricky, so be careful here. Negative 54 minus negative 46 is really plus 46. Negative 54 plus 46 is negative 8. So we get our answer for A, that's negative 4. So I know we're using A and B instead of X and Y, but you can think of the A like you would X. And now let's solve for B. So you can plug into either one of these, doesn't matter. 3 times negative 4, I'm going to use the top equation, plus 5b is negative 27. This is negative 12. Okay, add 12 to both sides. And we're going to get negative 27 plus 12, which is negative 15. So we get our answer for B, and that's negative 3. So the answer for example 3b will be the ordered pair negative 4, negative 3. All right, I got one more example. This is one of those cases where you could choose, it really doesn't matter, you could choose to eliminate x, it's going to require multiplication, or you might choose to eliminate y. It really doesn't matter. You can probably see at this point that using that same number, it's going to cause both of these to eliminate. Let's see what happens. When we multiply by 5 on the bottom and not do anything to the top, we get negative 35x plus 40y is equal to 55. this becomes 35x minus 40y is equal to negative 55. Well, it's pretty obvious what's going to happen here. Everything eliminates, and once again I'm left with a true statement. 0 is equal to 0. So anytime you eliminate and you're left, the final result of your elimination is a true statement, then the way we finalize our solution is by saying there's an infinite number of solutions. And let me just back up. If you should ever get to this point, everything cancels, both variables are canceled, and you're left with a false statement. This is true no matter what method, whether it's substitution or elimination. I'm going to change the problem here. Maybe you ended up with something like this. I know it doesn't match, but just pretend for a second. If you ended up with something like this, which is not true, then your answer would have to be no solution. Okay, so a true solution, true equation after variables cancel is interpreted as this. A false equation after variables cancel would be interpreted as this. So in this particular case, it's true. So we're going to say there's an infinite number of solutions. Okay, I hope that helps. Let me know if you have any questions.